No problem, take your time.
Sorry, technical difficulties, just give us a minute.
Can I start? Yeah. All right. Good evening, everyone. My name is Janani, and today I'll be giving a talk on galactic astrophysics. It's not working.
Is this button?
Yeah.
I need to plug in the chat with the PowerPoint. And then you need to go to the PowerPoint. And yeah. Okay, now you can type.
No, it's not working. It's not working.
Oh yeah. No, it's working now. I think.
No.
Eh?
No. Shall I just control from the laptop?
If you can. Microphone laptop, I think.
So it's just as normal, right? No problem. So I'll just stand here. Is that okay?
Yeah, yeah. As long as you can
Yeah. All right, we're back. I'll be using the laptop. So let me start again. My name is Janani, and today I'll be giving a talk on galactic astrophysics. I don't know. All right. In 1995, for 10 days straight, the Hubble Space Telescope stared into a tiny patch in the night sky, around the size of a grain of sand, thinking it's staring into absolute oblivion, right? But the results obtained 10 days later were nothing short of magnificent. The image you see here contains almost 3,000 galaxies, all encompassed in the size of a small grain of sand. This is also known as the Hubble Deep Field image. In the 20th century, astronomy started to take a strong hold among scientists. They were just trying to figure out about our Milky Way galaxy itself, but there were other fuzzy, incomprehensible objects in our night sky that we just weren't able to put our finger on. And the picture you see here is a very blurry image of Andromeda. And back then, we did not know it was a galaxy, so it was termed a nebula. But the true nature of this blurry nebula, the debate amongst it never seemed to cease. In the 1920s, there was a great debate that marked the true nature of what the Andromeda Nebula actually was. There were two sides to this conversation. One, Harlow Shapley, believed that this was in fact a nebula within our own galaxy itself. He voiced the feelings of the 17th century philosopher Immanuel Kant, who believed that this Andromeda was in fact an island universe, a sea of stars away from our Milky Way galaxy. The second image right here is of Herbert Curtis. He believed that the image we see here was not in fact a nebulae, but an entire galaxy of its own. He cited evidence regarding the frequencies of the novae observed in this small blurry patch, and he also brought up the fact that there were bright and dark lines that were observed in this image. The irrefutable evidence came from Edwin Hubble himself when he calculated the distance between Andromeda from us, from the Milky Way galaxy. And he observed and made these calculations through the Cepheid variable pulsation rates. Safe to say, Curtis won the great debate and the modern world got introduced to galaxies. So tonight we will be learning about galaxies, the different types of galaxies and their characteristics. Secondly, we'll be looking at some case studies, putting into effect what we've learned, more specifically looking at the Andromeda and the Milky Way galaxy. We'll also be looking at new observations and modern discoveries that we have learned from the James Webb Space Telescope expedition, and we will see the effect that these new discoveries has had on our understanding and knowledge of our great universe. So, moving on. First part, galaxies, a not so short introduction. First, I'll start by defining what a galaxy is. A galaxy is a huge collection of gas, stars, and star systems all held together by gravity. There are 4 main types of galaxies, and through our decades of observation, we have cataloged them. They are the spiral galaxies, the elliptical, peculiar, and irregular. Firstly, we'll be looking at spiral galaxies. They were coined by Edwin Hubble, and they are flat rotating disks of stars, gas, and dust. It has a bright center called the bulge, which contains a high concentration of much more older, redder stars. And this is surrounded by an extended halo of more fainter and also older stars. The main attraction of the spiral galaxies are, of course, their long sprawling arms. There are 2 main types of spiral galaxies, the normal spirals and the barred spirals. The barred spirals, in comparison to the normal spirals, have a rectangular shaped bar of stars that extends across the center of the galaxy. Our Milky Way is an example of a barred spiral. The spiral arms we observe here show ongoing star formations and are much brighter than the stars surrounding the center. And some spiral galaxies have more choppier, patchier arms, and they are called flocculent spirals. However, the way we observe the galaxies depend on the angle at which we can see them. When we see them head on, we can truly see it in all of its magnificent glory, with its sprawling arms rotating around and the pink and the glowing pink and blazing blue beads that dot the arms, right? But if we see it on its edge, we can see the interstellar gas and dust kind of marking the edges of the galaxy, in a sense bisecting it in half, and the top of the bulge just glowing, like, it's similar to a sunny side egg. Secondly, we'll be looking at elliptical galaxies. As its name suggests, they are elliptical in shape, and they don't really have a definitive shape and are more similar to giant puffballs of gas, and it ranges in different sizes. Compared to spiral galaxies, elliptical galaxies have much less interstellar matter, and they lack in gas and dust, and they are generally populated by much older stars. And they have fewer younger stars, which leads to the lower rates of star formation, and are dominated by older stellar populations, giving it more of a reddish hue. Peculiar and irregular galaxies, like its name suggests, have unusual shapes and structures. They are mainly formed because of galactic collisions. Irregular galaxies are completely shapeless, and they are shaped in a very small and chaotic fashion. We'll be looking at galaxy morphological classification now, and it is a system to help group and organize the different galaxies that astronomers over the years have catalogued. We'll be looking into 2 main different types, the Hubble sequence and the D-vacuolar system. The Hubble sequence, also known as the Hubble tuning fork, is a scheme that divides the galaxies into 3 main broad classifications based on their appearance. As you can see, the ellipticals and the normal spirals and the barred spirals. The letters refer to the type of galaxy we observe, and for the ellipticals, the numbers refer to the ellipticity, which is determined by the minor and major axes. The D-vacular system can be considered as an extension of the Hubble sequence. So the scientist D. Vacuolus, he argued that the spiral galaxy classification in the Hubble sequence was only based on the tightness of the spiral galaxies, or the how big of a bar they have, or if or not they have a bar. And he felt that it did not adequately describe the true and full nature of spiral galaxies that we observe. So he made his own. And his system basically elaborated on the Hubble sequence, adding more clarifications to the different types of spiral galaxies. I would like to show a video, but before that, I will just talk about formation of galaxies. So this is just a very short description. Galaxies are assembled from the bottom up, and they start off with the small clumps first and merge to form more larger clumps of gas and dust. So earlier in the formation of galaxies, it's very messy and chaotic, and there's a hot soup of gas and dust where star formation was very furious. And when the clumps got together, they spin in whirling disks, and these violent convolutions that we see settle down into density waves and then become spiral arms. So can I show the video? There's some sound.
That's not for my laptop.
No,
It's
it's
pretty
okay.
loud.
Yeah. So how do I click play?
The deeper we look into space, the farther back we see in time.
Light travels 670 million miles an hour, but even at this speed, light from even the closest big galaxies takes millions of years to reach us.
Looking deep is looking back, back to when the universe was younger. Right now, our best tool for viewing the young universe is the Hubble Space Telescope.
This is Hubble's deepest view into space, known as the Hubble Ultra Deep Field. Here, astronomers have found galaxies so far away that their light began its journey to us more than 13 billion years ago.
We're seeing these galaxies as they were when the universe was just 600 million years old.
In human terms, this discovery is comparable to a teenager looking at a 6-month-old baby.
But for these galaxies, the universe was no nursery. It was more like a brutal football game.
The earliest galaxies were small dwarfs, smaller even than the ones Hubble has seen. They grew by colliding and merging with other small galaxies, as shown in this simulation.
Over billions of years, these mergers built up the giant galaxies we see today. Mergers triggered pulses of star formation that created the elements necessary for planets, and ultimately, life. But to see beyond Hubble, to witness the origin and development of galaxies,
So that's this short simulation on the formation of galaxies. So we're moving on to studying and knowing a bit more about galactic spectra. So the information we know of the galaxies comes from the analysis of the galactic spectra. To what may seem to be a bright, unassuming fuzzball, through spectral analysis, we realize that they are actually whole galaxies. Galactic spectra helps us to categorize the different types of galaxies and helps make sense of it all. So it gives us information on the galaxy's velocity, the mass of the galaxy, star formation rates, and the relative age of the galaxies, right? To understand what the spectra is trying to tell us, we need to know a bit more about the three main characteristics: the continuous spectra, or the continuum, absorption lines, and the emission lines. The continuum is a combination of many black body spectra we obtain from the stars and the galaxies, and they span a different range of temperatures. We can notice the continuous spectra to be these squiggly lines in the spectral diagrams. And the wavelengths and their corresponding temperatures show the types of stars that exist in the galaxy. So a red color is indicative of a more older stellar population, whereas the blue color more younger, and shows evidence for active star formation. The absorption lines are characterized as sharp drops in the continuous spectra, and as we know, continuous spectra. So as we know, the galaxy is filled with interstellar dust and gas, nebulas and stars, and they all contain atoms, right? So these atoms, when they absorb light at various wavelengths, and when we take a look at this in terms of the spectra here, we see that certain wavelengths of light, they are being absorbed, and using this information we can find out the elemental composition, what atoms are the exact ones that are responsible for the absorption at this particular wavelength. And this allows us to correctly identify what kind of elements are present in the stars and galaxies. The emission spectra is kind of the opposite of the absorption spectra. So younger stars, they are initially encapsulated and covered in gas. So these hot young stars ionize the gas that it surrounds, and this causes the gas to go to, or the electrons in the gas that we see go to get excited to a higher energy level. So when they go back down to the ground state again, it emits energy at specific wavelengths, and that is shown by the colored lines in the spectrum. And when we and we can calculate the energy in that, and we can then pinpoint out which exact element is causing these emissions. Since we've been gathering data for years and years now, we've been able to catalog and organize these wavelengths of the elements that are responsible. And using this information, reading the spectra and analyzing them is just the next step. So we'll run through like a quick example, or just like a small case study. So this is the M101 galaxy, and if you see the pink regions here, the pink regions are the main areas where the hydrogen spectrum is seen. So HII is a region where the hydrogen gas gets ionized, and that's the place where star formation takes place, and it gives a great environment to study about this. And it contains often young and bright stars. And using the Rydberg formula, we can calculate the energy at which they emit the light in. So how much light is absorbed depends on the temperature and the atmosphere of the star we're studying. So the levels of absorption depends on the kind of star. So cooler stars, for example, are much smaller and they live longer. And their fusion from hydrogen to helium is at a lower rate. So as our star gets hotter, we get to know their absorption, their peak absorption level, and the sweet spot for maximum absorption are usually type A stars. So the measurement of the galactic spectra, the absorption emission lines, helps us to find out what kind of stars are present in a cluster in a galaxy, and it helps us find the age of that cluster, eventually allowing us to find the general mass distribution of the stars and galaxies. And through this, we can find the mass to light ratio, and it helps to measure how much light one detects when we work out the mass, when we can work out how massive the galaxy actually is. So without going into too much detail, another important facet in analyzing spectra is the 4,000 angstrom break. So where the break occurs is at the 4,000 angstrom wavelength, and by finding out how strong this break is, we can find out what kind of galaxy we're exactly observing. So elliptical galaxies have a much sharper drop at the 4,000 angstrom area, and spiral galaxies have a much more weaker drop. And this shows that it has a much higher population of both young and old stars. So if you see irregular galaxy spectra, for example, they have almost no angstrom. They have almost no of a 4,000 angstrom drop. So we know that it has a higher population of more younger stars. So before we move on, just a quick recap, and this poster is a very good recap. So the continuous spectrum contains all wavelengths of the light we obtain from the source. The emission spectrum only shows the colored lines at which the elements are emitting the light from, or the energy. And the absorption spectrum shows the dark lines or gaps from which the light passes through the gas. Now, let's take a step back looking at our galaxy. So we don't just exist by ourselves. As we know from the introduction that we have a neighboring galaxy called the Milky Way galaxy. So we are part of a smaller community of galaxies called the local group. The local group is an elongated, almost dumbbell-sized, dumbbell-shaped structure. And if we take another step back, these local groups form, they group into form these clusters called more clusters that they're part of another larger community. So our local group is part of the Virgo cluster, and these clusters are part of even bigger clusters. So smaller clusters like our Virgo cluster come together to form superclusters. So we're part of the Virgo supercluster. And the story doesn't end there. Virgo supercluster is also part of a much bigger community, which we call the Laniakea supercluster. We've now reached part 2 of the presentation. So we'll be looking at a small case study into the Milky Way galaxy and its neighbor, the Andromeda galaxy. So the Milky Way galaxy is where we live in. It's almost 10,000 light years across and a few thousand light years thick. Like we've learned before, it's a barred spiral galaxy, and it has two major arms and 2 minor arms. The bulge, if we consider the bulge to be the city center, then the Milky Way, the solar system exists in the suburbs of the Milky Way galaxy, about 25,000 light years away from the center. So if we ourselves live in the Milky Way, how do we know exactly how big our galaxy is, and how do we basically know anything about it? So for a really long time, astronomers believed that the solar system was at the center of the Milky Way galaxy, and we obviously had no way of telling. Eventually, we studied globular clusters, and they are spherical balls of stars that orbit the galaxy well outside the main body of it in the halos. So through observing the night sky, it seemed that the globular clusters had a higher concentration in one side of the night sky compared to the other. Does that mean that it's not evenly distributed? No, it actually meant that we were not in the center. We were actually off center by almost 25,000 light years away towards the direction of Sagittarius. And that's why if we take a look at a completely dark sky, we can see the glow of the Milky Way, and that glow kind of gets brighter towards the direction of Sagittarius, because that's where the bulge is. Radio astronomy helped astronomers get an idea of the structure of the Milky Way galaxy. So star-forming clouds emit radio waves, and it can be used to measure their Doppler shift, through which the velocity and relative distances could also be found. Analysis of the nebulae indicated to us that the galaxy or the Milky Way galaxy is split by long spiral arms that wound around, and exactly in between the arms they observed virtually no presence of nebula, so stars or galaxies, and this kind of strengthened the idea that it's a spiral with arms kind of spiraling around. Another key mission which helped us map the Milky Way galaxy was the Gaia Enceladus mission. The Gaia satellite was able to pinpoint stellar positions, and that enabled us to detect the tiny motions of the stars. Astronomers used this data to reconstruct the detailed orbits of the stars. And the findings of this study, which I won't go into much detail, helped give us information about how our Milky Way galaxy came to be. And like the video showed, it's formed by the mergers of other nearby stellar entities. For example, the Milky Way galaxy we see right now is caused mainly because of the merger of the Milky Way galaxy 8, a nearby galaxy which is the Sagittarius dwarf galaxy. It's also observed that the Milky Way galaxy is also going to have its big lunch in about 2 billion years because the large and small Magellanic Clouds, the satellites of our Milky Way galaxy, they are currently making their first pass through our Milky Way galaxy, but the full merger will only happen about 2 million years later and 2 billion years later, and astronomers predict that it will completely change the way how the galaxy looks like. Now, one can think of the spiral structures as large collections of star nebulae that move together. But if this were the case, it would be akin to like a ball of yarn eventually rolling back into its center. But the spirals don't wind back up into the center. So a better way to think about the spiral arms is to understand the idea that they are like traffic jams. So this traffic jam may be created by some kind of disturbance, like a collision, a small collision, for example. And this disturbance then spans out, and because it's rotating, it curves into the spiral we see. And when other stars and gas and nebulae enter this disturbance, this wave, it's much like incoming cars entering into a traffic. They stop, they move on, they accelerate, or they slow down, but eventually they do cross the traffic jam. But the traffic jam still persists. So a more scientific description would be that the arms are waves made up of different objects, but the objects themselves are transient. So the Andromeda galaxy is our neighboring galaxy, and we remember her from the great debate when the astronomers were debating whether she was just a nebulae or a galaxy. It's the biggest galaxy in the local group, and it's around 220,000 light years across. And its stellar population greatly exceeds our own, as it has stars in the trillions. So we're going to talk about galactic collisions now. So Andromeda is on its way colliding at us at 110 kilometers per second, sorry. And around 7 billion years' time, the Andromeda and the Milky Way will collide. When the first collision occurs, the spiral structure of the galaxies are completely disrupted, causing them to stretch out into large curves because of the tidal effects, and it will become what we call as tidal tails. And the next few million years, they will pass by each other and collide until they eventually finally merge into a much bigger elliptical galaxy. And the scientists have given the galaxy a very unique name, Milkomeda. So I'll just show a simulation of it. Can you show?
The only way to do it is to automate it. What Zapier allows us to do is connect to our customers' Shopify.
Yeah, there's no volume in this. Oh, there's no volume in this, John. Yeah. That's the timestamp there. So this is when they collide, and the structure is completely disrupted, and they will just pass and go until they finally merge into one big galaxy. This will take, of course, billions of years' time. Oh, that's a triangulum galaxy. Yeah.
Will the sun die first, or will the collision happen first?
So that's still a very, they're still learning more, like analyzing more about it, but there's a chance that our sun and our solar system will not be affected by this, and it might just rotate lazily around whatever direction it's pushed in, either further away from the center or towards the center. but that's much, much later. We might not even exist. Yeah. So the Earth might still be there when it happens, but we might be completely unaffected by it. The Andromeda also, like our Milky Way galaxy, is a very big black hole right in its center. So during the collision, if these two black holes collide, it'll form a super, super massive black hole, and it'll gobble up any interstellar star formation gas. And we might temporarily power a quasar, and we could become an active galaxy. So finally, we'll be looking at, is there any new information that we've learned? So right now, the James Webb Space Telescope was released a few years ago, and it has been collecting data about other galaxies, way back in time, looking into the past, right? It has a more sophisticated design, which allows us to study the universe at its early stages. And compared to the Hubble Space Telescope, the JWST can view almost 12 billion light years back into the past, and it does so because it views everything in infrared light. So the main reason why it's an infrared light is so that we can be able to study galaxies in the early universe. So when the light comes to us, it's essentially stretched out so much that we only see everything in redshift, that it's redshifted to where it has a very high redshift value. So when we use the infrared light, when we analyze it through the infrared spectrum, it allows for a better viewing of the dust and stars, and we get a better view of the earlier galaxies, and we can slowly complete our map of the cosmic evolution. So there was a few news articles which became really popular about the James Webb Space Telescope discovering these 6 ancient galaxies that clearly should not exist because they completely go against what we know as what we know about our models that we have right now. So as always, the media likes to blow up and skew things. And these galaxies which existed, these are the 6 ones over here. These galaxies existed when our universe was only a few 100 million years old. And basically, how do we know more about galaxies? We use galactic spectros. We've learned that before. So as of now, the paper which released the images and about these galaxies, they haven't had a spectral analysis yet. And because we haven't been able to properly analyze these graphs, the information that we do have about them might be inaccurate, especially in regards to their stellar mass distribution and their distances from us. So we've only used approximation and best fittings with our existing models. And even though it gets us some values, they are merely estimates and we cannot take them to be accurate. However, with these estimates, these galaxies we observed have been able to get an estimated mass distribution that is similar to our Milky Way galaxy. It's interesting because these galaxies, which are 750 million light years after the Big Bang, are already well developed like our own Milky Way galaxy, when the universe was still back then what we think to be just a hot mess. And it took 13.8 billion years for our Milky Way galaxy to reach our current state right now. So how are these galaxies just in the very early stages of the Big Bang, how are they already so established? So if these numbers are accurate, we right now don't have an explanation for it. Why do these galaxies exist, or the nature of them? We don't have an answer to it. Is this a paradigm shift in the knowledge we know? We might never know. Star formation in simulations that we do at home take a slow and steady rate because they're based on the current models that we do have. So the new data definitely may not fit into our existing models because they are newer data. So this doesn't mean that what we have is wrong. It doesn't mean that we should throw away our ideas about Big Bang or the lambda cold dark matter model out the window. We should not scrap our existing models, but we should use the new information to fill up the gaps and holes we have in our knowledge. The early universe was a much different environment than we have right now, so star formations could happen more efficiently at a much more different rate compared to what's happening right now. So the James Webb Space Telescope's job is to learn more about earlier galaxies and hopefully help us come to an understanding, or at least try to understand, how our universe was evolved. Thank you.
And so thank you, Janani, for the talk on galaxies.